Let's now go over concrete examples on how we can restore the tree balance using rotations. And let's first of all talk about after insertions, and we'll talk about deletions later. And for insertions, we actually got 4 different cases that you may have to perform. Which one to apply, you have to judge, of course. But let's now learn the best, maybe by examples. Let me just go over with you one slide with a bullet point just about general principles, and then we'll apply them on the concrete example for each case. After inserting a new end, we may or may not compromise the height balance property. So that's why we have to perform rotations whenever necessary. Case number 1. If along the ancestor path of the node being added has no node that actually become unbalanced, in that case, you just don't need to perform any rotation. I would say that's the lucky case, but you may not be lucky every time. So that's why we have to judge. But for case number 1, we actually did some example earlier, if you can recall. Let me just show to you very quickly. If you recall from the earlier part, when we spoke about the high balance property earlier, and actually the case where we actually, after inserting the node with key 63, in this case over here, the tree actually remain balanced. That's what we said earlier. So in this case, no rotation will be needed. On the other hand, in this case over here, after inserting 55, the tree will become unbalanced along some nodes on the ancestor path, right? So that's why you have to judge. But the cases I'm gonna show to you will be all the cases where rotations will be needed. Let's take a look. What about case number 2? Case number 2 will be, well, at least one node along the ancestor path becomes unbalanced. In that case, you have to identify them and then perform some rotation. And the rotation can be to the right, as we illustrated before, or it can be to the right, or to the left, or it can be maybe some the so-called double rotation, in which case you're going to perform left followed by right, or right followed by left, and etc. So you want to get let's just go over principle, and I'll illustrate to you exactly how to perform these. Get the first and lowest unbalanced node along the ancestor path. Basically, just go up on the ancestor path from the node being inserted. As soon as you identify the very first node that becomes unbalanced, in that case, you're going to perform the rotation. And then you want to name from there. So once you fix the node that's become unbalanced as A, you're going to fix B and C accordingly as their child and grandchild nodes along the ancestor path. I'll show to you a little bit later, visually. And you want to perform the rotations based on the alignments of A, B, and C. And there are two sub cases over here. Either they actually slant the same way. They might all slant to the left, or they might slant all the way to the right. In which case, a single rotation on the middle nodes will be necessary. So these are the 2 cases I'm going to show to you first, which require only a single rotation to restore the balance. And if they A, B, and C, they slant in different ways. Maybe they slant to the left and then to the right, in which case you will need 2 rotations to actually restore the balance. And the starting point for the rotation will be the lower node as opposed to the middle node. Right? Just notice the different terminology we are using over here, and then just notice the details that might actually require for you to perform the rotation. And in the lecture, we're just going to focus on the visual illustration about how the rotation should be done, and it will be up to you to really implement it in valid Java code. And to really do the rotation, it turns out to be very cheap operation running time wise, because you just have to set the parents and child references accordingly, according to the visual illustration. For that part, I'm going to rely on you beyond the lecture. Alrighty, so let's now go over the 4 cases one by one.